My name is Shiva Singh. I am your Prime Minister's Research Fellow Teaching Assistant for this Metal Mediated Synthesis 1, and I will be solving the assignment number 1 for week 1 of the previous session. As your due date of the current session is not came yet, so I cannot solve those questions. For this course, Professor Debabrata Maiti is course coordinator from Department of Chemistry, IIT Bombay, and my PhD is supervised by Professor Pradeep Kumar Maji and Professor Kaushik Ghosh jointly at IIT Roorkee. Before starting this presentation, I shall introduce myself and I shall tell you what this presentation or session will be consisting. Okay, firstly, give me a minute. Someone is, yeah, fine. Yeah. So, firstly, I will be giving my brief introduction. Then, I will be giving you some questions and the solution of those questions. And I will also discuss the basics involving in it and the explanations with them. My name is Shiva Singh. Currently, I am enrolled as a Prime Minister's Research Fellow at IIT Roorkee, and I will be assisting you with this Metal Mediated Synthesis 1 course. Regarding this metal mediated synthesis, I have worked in metal catalysis with Professor Akhilesh Kumar Verma at Department of Chemistry, Delhi University, in which I have done cross-coupling reactions, which you will be learning later on in this course. I have also done total synthesis with the Professor Alakesh Desai at IISER Bhopal, Department of Chemistry, and recently I have done my masters from VNIT Nagpur with Professor Chayan Das. This is my brief introduction, and I should also enlist some of my achievements which I have gone through during my career from graduation to post graduation and now in PhD. I was an inspired scholar from graduation to post graduation 2014 to 2019. I was also selected as an SN Bose scholar. I qualified GATE. I am also an Inspire Junior Research Fellow. And in the end of 2020 December, I got selected for the Prime Minister's Research Fellowship. So, this is your assignment 0, which have been given in the current session, and it do not constant any marking in your course. So I have solved the questions and I will be giving the basics and the mechanism involved in it, because chemistry is all about the mechanism. The more you understand the mechanism, the more you understand the chemistry. So the first question is, Wilkinson's catalyst is commonly employed in what reaction? The answer is hydrogenation. This is the structure of your Wilkinson catalyst. It is a square planar uh, catalyst of rhodium. While starting its catalytic cycle, initially what happens, these the phosphine ligands, one of the phosphine ligand gets dissociated and the square planar geometry gets distorted and creates a vacancy. In this vacancy, oxidative addition happens, in which the oxidation state increases by +2. While inserting this hydrogen, uh, octahedral type complex forms with one vacancy. This vacancy interacts with your alkene, which is supposed to be hydrogenized, and after that, this octahedral complex forms. Further leads to the 1 to insertion, means one hydrogen migrates here and this interacts with this rhodium. Again, a vacancy comes and reductive elimination occurs. The hydrogen goes with this and alkene goes out, and again your reactive catalyst is generated. This catalyst keeps on involving in this cycle again and again till there are some conditions. Either quenching occurs. Quenching means either we remove the inert environment, that means some oxygen or moisture comes in the system, the reaction stops, or this reactants, either of the reactant if not available in the reaction, that means it is consumed, the reaction will not proceed further. So these three are the conditions to stop this catalytic cycle. Otherwise, this catalytic reaction will keep on happening theoretically. If we go to the next question, in a metal alkyl compound, which sigma bonded R group could undergo beta hydrogen elimination? So we have these options. To discuss this, it is the first option. I should actually this discussion is also available in YouTube. I have previously gone through a dry run for this session, and the link must have been provided to you. Otherwise, later on, you will get a link from my channel. The first video of my channel is the discussion of this session. So, I will be taking it briefly as I have already discussed it. So, I am expecting that you will go through that and ask me the queries in the later sessions if there are any. So, suppose the first option we have ET. Okay, so this is our metal, right? Carbon, carbon. Okay, this is your ET group, right? So the first position from the metal is called alpha. It is the beta. These are the beta hydrogens. This beta hydrogen can interact with the metal, can go here, and this bond will break. So what will happen? A double bond will form. Okay, this ligand and metal will be here, and it will be interacting with this alkene. Fine. This will be your beta hydride elimination. If we see in the second case, this is the second case which have been given here, CH2PH. So this is the alpha position, this is the beta position. If we see, one, two, three, four, four valencies are complete of the carbon. There is no beta hydrogen, so it cannot occur. In the next also alpha, beta, and again we can see beta position, we do not have any beta hydrogen, so it cannot occur. Similarly, we do not have any beta position in this case. Again, if there is no beta position, there is no chance to get any beta hydrogen. That means it can also not occur. So our right answer is ET. If we proceed for the next question, the order of the reactivity of alkyl halide towards oxidative addition. What happens with the oxidative additions? That means there is a metal, okay, AB some compound, right? It will go to the metal. Metal is in, suppose, just consider it is in zero oxidation state. It will come here, and this is the metal, and A and B, the oxidation state increases by 2. This is called oxidative addition. So we have here RCl, RBr, Ri, right? So the more tendency to get attached with the metal is with them who are weakly bonded. That means if this bond gets break easily, it will be easily bonding with the metal. So if we see here, R means it will be having a carbon, right? Carbon iodine, okay? Carbon bromine, okay? Or carbon chlorine, right? So if we see the size difference, they have the biggest size difference. Easily means least overlap. Least overlap means easily breakable, so it is more prone. Then same case with the bromine, smaller than iodine, a little bit better overlap, so it is on the second. And these are in the same uh, group, so they will be having almost equal overlap, so they will be the least breakable. That means this order is the perfect order, and I have also given some explanation regarding this here. You will be provided with the presentation of this and the video link on the YouTube, right? Singlet carbene has a pair of electron in sp2 orbital, one single electron in sp2 orbital, a pair of electron in sp3 orbital, and a pair of electron in sp orbital, right? So if we see here, this is the singlet carbene, this is the triplet carbene, and it is its electronic structure. This is the sp2 hybrid orbital, and we can see here we have a pair of electrons. In the triplet carbene, parallel parallel electron pairs, they cannot do the pairing, so it cannot be here. That's why it is triplet carbene. It is a singlet carbene having sp2 orbital. Sp2 orbital is having the pair of electron in the singlet carbene. Okay, we shall go forward to the next question. In a spontaneous reaction, dg value should be, don't get confused, it is that dg gives free energy, right? Positive, negative, zero cannot be defined. We all know we need negative delta G value for the spontaneous reaction. That means a reaction will be spontaneous when, if we do not supply any energy in the system and still reaction is going on, that reaction is called spontaneous, right? So we have few cases with respect to this equation. I shall explain this. Either delta H can be negative, positive, negative, positive, or delta S positive, positive, negative, negative. Okay. So if we have delta, one thing more, the temperature here, this temperature is Kelvin temperature. That means it never goes to negative, right? Okay. So it will be always positive. Consider this for all the time. I need not to repeat it again and again. Okay. So if we see delta H is negative, means our equation first part is negative, right? Delta S is positive minus, there will be some temperature that is positive multiplied by some positive entity, again minus and minus, it will be giving minus delta G value. That means negative value always spontaneous when delta H is negative and entropy is positive. Fine. So if we go further, suppose we have delta H positive, that means, and delta S also positive, what will happen? The first step will be positive, the second one be minus, positive into positive, right? So it, this entity can be either positive or negative, in which case if temperature is higher, suppose the temperature is higher, it will cross the delta H value. If it is crossing the delta H value, it will be spontaneous reaction. Okay, that means negative at higher temperatures, right? And positive at lower temperatures. That means if T value is positive, means T value is lower, and it will be smaller than delta H value, then the delta G will be positive and non-spontaneous reaction will occur. Similarly, delta H negative, that means negative here. Okay, second term negative into some temperature that is positive and overall negative, right? This is the term, suppose this is delta H. Okay, so if we see here, there are again two cases, negative at lower temperatures. If temperature is lower, it will get to positive, but it cannot overcome the delta H that is negative, so it will be spontaneous. But in the case of higher temperatures, delta S will become positive and higher than delta H value. So what will happen? It will act as a non-spontaneous reaction. Again, delta H positive, okay, delta S negative, and the negative term is already outside, so negative, negative, positive, this is positive, this is positive, overall positive. So delta G will be positive, that means non-spontaneous reaction. We shall go to the next question, the IUPAC name of the following compound. I shall tell you that in this question there is a doubt situation, because if we see here, whenever we do IUPAC nomenclature, as per my best knowledge, we need to see the longest, sorry, longest carbon chain, right? So this is the longest one, if we see, and it is having only 8 carbons. So no 9 is difficult to be here. According to my view, it should be, if we do the numbering, 1 2, right, third carbon, fourth, fifth, sixth, seventh, eighth, the longest chain is 8, right? And third position and sixth positions are having methyl groups, that means 3 6 dimethyl. Okay, at fourth position it is ine, so fourth and 8 carbon chain octane, right? So this will be the answer. I hope you have like heard me, because my writing is not good. Again, I should write it properly. 3 6 dimethyl 4 octane, and I think it is now readable. Okay, we shall proceed to the seventh question. The high coupling reaction in olefin insertion step. Oxidation state of the palladium will change as. So if we see, this is the olefin insertion, right? We start from here. Whenever the oxidative addition occurs, plus 2 oxidation state increases, and now when the olefin inserts, what will happen? This will form a bond with double bond, right? But the oxidation state will not change. How? What will happen? This R will go to R2 and this bond will form. Okay, we can say here, see here, and this hydrogen will again move here and this bond will break again. The similar situation as here will occur, and beta hydride elimination will happen. We will find the coupled alkene, and to regenerate, BHX will be used, and again the regeneration of this catalyst will happen, and same three conditions of the catalyst, that means quenching. If quenching occurs, then only it will stop, or our one of these gets fully consumed in the system, right? So this is your answer. That means, sorry, this one is the correct answer. Fine. Sorry. Okay. This is our eighth question. How many equivalent of Grignard reagent is generally used in the Klonikowicz reaction? So if we see here, from here the reaction start, two equivalent of the Grignard is used here for the formation of this. C2H6 goes out, and we have this propane type of arrangement. Again, the reactive species gets involved, and a five-membered ring formation occurs. And here is the our product, right? So product goes out, and 2 molar of RMGX, that is your Grignard, is used to regenerate this catalyst, but it is not used in the reaction. So that means only 2 mole of the Grignard is used overall in the reaction. Again, the hydrolysis can be done, and this will uh, where is the reason? Actually, this bond will hydrolyze during workup, and we will find this as the product. Fine. So two equivalent of this Grignard reagent is used in each cycle of the reaction. And again, the ligand will, the catalyst will be regenerated, and the reaction cycle will keep on happening till only those concepts, either this or the quenching of the catalyst. Fine. The valence electron count is usually associated with the stability when thinking about transition metal organoids complex. So here the answer is 18, because S, P, and D orbitals are the valence orbitals of the D block elements, right? So if we see 5, okay. But there is a special case which I haven't mentioned yet. In square planar geometries, the orbitals get splitted and they are more stable at 16 electron count. You will be studying in the later on stage. But for the general idea, or usually, 18 is the correct answer. Fine. So organotin is used as the coupling partner in Kumada, Suzuki, Stile, or none of the. Stile was the scientist who used tin as the catalyst in the reaction. Oh, sorry. Fine. Right. This is your assignment 0 of this session. Now I will be proceeding for the assignment 1 of the previous session. I would expect the answers from you, then I will explain if you cannot explain the answers, right? So, right. Yeah. This is the question. In asymmetric hydrogen reaction, the major enantioselective product results from minor substrate catalyst, diastereomer, right? Minor enantiomer in substrate, major substrate catalyst, diastereomer, and major enantiomer in substrate. Okay, so come on, reply in the chat box. You have 1 minute for answering this query, and then I will be explaining it. Right, time starts now. Come on. I want it to be an interactive session. More you will interact, more you will get to know. Okay, 1 minute is over. No one is able to answer this question. Fine. Right. Hmm. So the answer is minor substrate catalyst diastereomer. I will tell you how or why. Can you see this mechanism? I shall make it bigger. Wait. I zoom this. Wait. No. How can I zoom this? Fine. It is not zooming at all. Fine. Fine. See. Right. Okay. See. If this is our chiral catalyst. Hmm. Okay. Now I cannot annotate. Fine. This is our chiral catalyst. You can see. Fine. You can see the hand on the screen, right? This is our chiral catalyst, and this is our alkene, which is supposed to. Okay, come on. Give me a minute. Fine. So here now it is working. This is our catalyst, chiral catalyst, and this is our uh, alkene, which is needed to uh, go to the hydrogenation, right? So if we see this catalyst is chiral, so it can get attached with your alkene in two manners. Either it will bound the alkene from re phase, right, or from C phase, right? So this is a like a reported reaction. I shall just tell you how it is going on, right? So the C phase formation occurs 90 to 99%, right? So and this only occurs 10.1 to 10%. Okay, so that means this formation is very stable, right? And this is least stable. So if we see which is least stable, that means the energy barrier. Suppose this is here and energy barrier is here. Okay, it is achieved, then the product formation, right? For this one, suppose it is A, it is the B, right? So if it is for A, this is here. For B it will go to higher and then the product formation, right? That means it is already stable. B is already stable, so if we want to get further product, we need to input more energy, right? So H2 will react with the less stable one or least form, which is formed from re phase. Okay, then one to migration migratory insertion will happen and your product will be formed, that is L-DOPA. Okay, but from this it will be least or minimal, right? 95% of enantiomeric access was achieved, right? So if I explain here, I have wrote the explanation. If you want, I can read it. The enantioselective step in oxidative addition of hydrogen to square planar diastereomeric substrate complex that are in rapid dissociation. This is your rapid dissociation equilibrium. They can move here and there, like either re phase or C phase. It will keep on happening. The major enantiomer of product arises from the minor substrate. Means if we are getting the major product, from where it will come? Minor substrate of catalyst diastereomer. It was shown by kinetical study that the minor diastereomer was 580-fold more reactive towards hydrogen. It is the rate determining step at the room temperature. That means kinetic study also support this mechanism. Fine. I think this can be understandable, and these annotations will be removed while I will be sharing the PPT with you. Okay. So no worries. Just to make you understand, I have done this annotation. Okay. Fine. Let's go to the next question. In Fischer carbene, metal center is in oxidation state, either low or high. And in straw carbene, metal center is in oxidation state, low or high. I shall get the answer from you. I think you will be able to answer this question. I'm waiting for one or maybe 30 seconds. Come on, ASAP. Answer it in the chat box. Okay, someone answered B. So low metal center is in low oxidation for Fischer and high in the straw carbene. Fine. Anyone else? Okay, we shall go further. So it's correct answer. This is a comparative study between Fischer and straw carbene. The carbon, generally electron deficient in Fischer, is stabilized by the heteroatoms like phenyl groups. Okay, and it will be generally attacked by the nucleophiles because it is electron deficient. Electron deficient means whenever there is a carbonyl, this carbon gets deficient, right? Electrophilic attack, or sorry, nucleophilic attack occurs here. Fine. So in this manner here also it will happen. And what will happen? Metal is in low oxidation state. Low oxidation state, that means electronically rich and attacked by electrophiles and stabilized by, if I have more electrons, and metal have tendency to give electrons. So that means if there is a group which is coming and having tendency to accept the electrons, okay, so those will stabilize these type of metals. Okay, similarly the like Just opposite case will be in the shock carbene. Fine. I think this is understandable. Now I can move to the next question. This is the next question. This is your metal center. This is your reactant. It will react with this substrate and there will be some product. And these are your options. I am waiting for your answer. I will explain it with the mechanism. So let's wait if anyone can answer. It's not a big deal. I have just previously explained something. Okay, I should mark it also. This is the key of your answer in the next question. Come on. See, okay. Again from Mohan. So she's saying it is C. Fine. Let's go to the next. So I have already made this explanation for you. See, it is the Fischer carbene. Okay, metal is low oxidation state. Fine. Wait. I shall change the color of this pen. This is good. Fine. Now, see, this is already in low oxidation state. Delta negative means slight negative charge, and it is having. This is our electrophilic center. This one, fine. So if we see our this reactant, phenyl and lithium metal, which is stabilizing this phenyl, right? It can act as a nucleophile and attack here. This bond will go here. Okay, and this lithium will stabilize this transition metal. So what will happen? This substrate will occur. Again this negative charge metal cannot occupy the negative charge on it, so what it will do, it will push back the electrons here. So what will happen, this phenyl are forming the stable bond, but this is the oxygen and Me bond, oxygen forming with the carbon, right? So this is a good leaving group, it will leave, and this lithium will stabilize this, and this is our product. So right, she answered right. Let's go to the next question. This is our question. This is the substrate, and we have this another molecule which will be reacting with the substrate. So for your understanding, I shall write it Na plus OMe. Sorry, minus, right? It is minus. Okay. Now it is for your understanding. I have made this. Now you have to give me the answer. This is the hint. Fine. I shall. Yeah. Okay. See, if we see here, this moiety acts like a base, isn't it? So suppose this is the metal center, this is CH2 CH3, this hydrogen can be abstracted by a base. So base took out this. Give me just 1 second for now. Okay, just a second. Huh? What has happened? Admit. Okay, fine. Yeah. Again, I shall go back to my presentation. Fine. It is visible, right? F5. We have already gone through this. We were actually here. No, it was also done. Yeah. So what is happening? This is our base. It is abstracting the proton. So methanol is coming out. What will happen? It will be having a negative charge which will come here, right? A double bond formation will occur, and this is your product. Nothing, not a big deal, not big chemistry, nothing at all. Just Simple concept that base takes the hydrogen, base abstract the hydrogen. That is what happened here. So your answer is fine. Any doubt? Okay, let's go to the next question. Which one of the following is Grubb's first generation catalyst? See, such type of questions in your exam, you will not be able to answer them with the concept. What you will have to do, you will have to learn, you will have to read. Just small differences are there in the Grubb's first, second, and third generation catalysts. So we can see here these are the three type of Grubb's catalyst: first generation catalyst, second generation catalyst, and Haveda Grubb's catalyst. Right? So tell me which one is the first one. So what is the answer? I have already given you the answer. Tell me the answer. We have the structures, we have the names also. You have to just match here. Great. B. We can see it easily. It is not actually what is happening. This is A. Okay. Let's try to understand. This is B. Okay. And this is C. Okay. And this is D. Fine. And now it is properly understandable. This is B, the correct answer. We shall move to the next question. And I have also given the advantages and disadvantages of these catalysts. So maybe some type of comparative question can come out in your sessions, like whatever exam you will be attempting. You should have conceptual approach also, that is necessary, but you should have approach to access a question. You should have the tendency first to decline the answers, that this cannot happen, this cannot happen, this cannot happen. If you can remove two options from four, suppose you can remove two options, we have A, B, C, and D, right? You have disqualified 2%, right? Now you have to apply your concept only on two options. That will be far better and easy approach for uh, getting a question, getting a proper answer in such type of questions. If you have four options and you will be applying your concept on four options, it will be your time taking process. So firstly, approach them with the elimination method. Eliminate, then apply your concept. It will save your time, but yes, concept is necessary. Fine. We have to go to the next question. Predict the outcome of the following reaction. This is the Krebs second catalyst, right? And I have explained it here. Whatever the advantages and disadvantages of this Krebs catalyst. So come on, tell me the answer. You have 1 minute. It's not a big question, not at all. Okay, the answer told by Hemavati Mohan is B. She is saying this is the correct answer. Anyone else? Fine, we should go to the mechanism. Yeah, surely I will be giving you a mechanism. Mechanism is necessary for any question. Let's go. Actually, what is happening here is ring closing metathesis. Here, ring closing metathesis is occurring. Okay, now she is saying the B will be the option. Okay, again I will say do the approach via elimination method first. First eliminate, then get the answer. Okay, now it's A. So if you will be attempting an exam, you cannot put three options. You will be having one chance only. You will be putting it, and it will be either right or wrong. First, do the elimination. This cannot occur anyhow. This will not occur anyhow. Let's do with these two. Okay. So if we see this is our Grubbs catalyst, right? What will happen? It will form a ring, right? So This will go out. Rhodium will stay with the complex. Again, the metathesis will occur. Four-membered ring will form, and five-member this ring will dissociate, and we will get minus Ru and CH2. Fine, and we will get this molecule. Fine. Now see, there is nothing, not a big deal and all, just it happened. Okay, if we want to get the catalyst back, that means the catalyst should involve in the catalytic cycle again. So what will happen? Again this ring formation will occur. Okay, and this is our minor product, and again regeneration of the catalyst. I hope this is understandable, the mechanism. So it is A. Fine. Okay, someone is in the lobby. Just give me a minute. I don't understand why right now. Like it's almost ending. Fine, we were here only. Okay, yeah, five. Fine. So we were at. What if I increase some time? Like it is 3:54. I want to finish these questions. I have already finished six question. I have four more questions. Fine. So predict the product from the following reaction. It is a beautiful question. It took a lot of time of mine also. Come on. I will give you 1 minute. Predict the answer. Uh, I will appreciate if you answer either wrong, right. No worries. I will explain it just in a minute. And I should tell you here also ring closing metathesis is occurring. Okay, fine. The answer is A. Anyone else? That's good. You are approaching. Okay, Raghav is saying D. Okay, Raghav, just tell me what is happening in this reaction. Like there is some specific mechanism or something is happening there. No idea. Okay, just don't go blindly. Okay. Oh, okay, okay. Okay, the show 1 minute is over. I shall go for the your answer. So if you see here, this is our substrate which will be reacting with this metal. Initially, what will happen? Four-membered ring, as I have shown here, will form, right? This ring formation occur, and we know whenever alternate double bonds are there, they will be in conjugation. So we can say it is here, right? It is here. So what will happen? Again, the we will find this molecule, right, and the metal is again gets attached with the substrate, and we can see here this and this can occur again metathesis, again four membered ring. Okay, and the simply bond breaking will occur. This is the rearrangement and bond breaking will occur. Okay, so once bond breaking will occur, this will be your product. Sorry for like the arrangement, the answer will be D. Fine. But if we see here, this is the product, but this part is from the alkene, right? If this part is from sorry, this part is from catalyst, but we need the catalyst in the next cycle. So what will happen? We need to regenerate the catalyst. So this and this part will react again, form a four membered ring, again the resonance and ring breaking. This is minor product and regeneration of your catalyst, which will involve in the reaction again. Fine. So now I think Mohan, you have understood why the A is not answer. You have did good approach. Just one bond behind. Okay, it is D. Give me 1 minute. Again, someone is there. You're presenting to everyone. Fine, fine. So just the we have the it is seventh question, and we have three more questions. So the trans-alkylation of two-terminal olefins accompanied by release of ethane is defined as. Do we have any answer? The transalkylation of two-terminal olefins accompanied by the release of ethane is defined as cross-metathesis, ring-closing metathesis, olefination, cycloaddition. Okay, the answer is B. Fine. The answer is already explained somewhere, right? This question is the same question. This is your metathesis, ring-closing metathesis, and this is one more. Okay, ring-closing metathesis already explained. Need not to explain this. Let's move to the next question. So, what is this reaction known as? As I have told earlier, not all the time you need the concept. You need to read also. So here you cannot answer. You have to know which is this reaction is. You have to see the catalyst, see the substrate, see the product. Then only you can tell. Oh, this one is that reaction, and it will occur in this manner. Okay. Can anyone have answer? Okay. Uh, Mohan is saying it is Kirchner cyclopropane synthesis. Okay, so this is cyclopropane. That's why you are answering this. Maybe. Okay, fine. So I shall say that it is not Kirchner cyclopropane synthesis. It is Simon Smith reaction. The carbon will attack here, and again this type of butterfly transition state will occur. Then Zn2 will be removed and cyclopropane will be forming. Okay, Simon Smith reaction. Fine. I hope it is clear. This is our final question, the easiest one. We have these two substrate at the presence of this is catalyst. It have no role but to enhance the rate of the reaction. And if you see this, you can just tell me what is this. This is a beautiful molecule for chemistry, right? It can be like this or it can be like this, right? So plus charge. Okay, stable molecule, nitrogen will be out. You will have some. Tell me what is this? Now you have the substrate. You do not have to do anything. This substrate will react with this bond, and here is your answer. I just want this name from you guys. Come on. We have discussed this only in the whole lecture. Yeah, carbene. This is the mechanism. Nitrogen goes out, your cyclopropane formation will be occurring. Fine. This is the formation of your carbene. Okay. Thank you very much for this patience, and I shall say that if you have any query, you have 2 3 minutes. You can write it, and I will be addressing them in the next session. Fine. Okay, I shall stop this meeting right now. Thank you.